There are other logic gates, of course, right? We have looked at the AND or negation, right? The inverter. We looked at that NAND gate, which is important. There is something called a NOR gate, which is this negated OR as well. But the one that I want to really explain right now before we move to something else is this one, the exclusive OR gate. And if you remember, I think we mentioned the exclusive OR truth table. This one is that one that is very similar to an OR gate, but the main difference is that it does not allow both inputs to be true, right? So I cannot have A true, B true, that will be false. So the XOR gate, right, exclusive OR gate, I want to propose something different. So I'm going to show to you this drawing of this circuit that in theory represents an exclusive OR, right? So which is this one right here. Pause the video and try to understand yourself how this accomplishes that XOR gate, right? Because it's a lot more interesting if you pause and you understand before I even explain to you. If you go and you follow the path of the current, right? We have probably this kind of OR parallel path here between A and B, and then we join with these two. See how we have this VCC, the voltage, right? The current also comes down here. This VCC, this voltage at the common collector, right, is the same as this one and is the same as this one. I'm just showing three different arrows here, but they are all from the battery, right, if you want to think like that. So this VCC enters here, the same VCC voltage enters here, and then depending on how these things are configured, depending on this A and B, then current goes and finds the ground or doesn't find the ground, or completes the circuit or doesn't complete the circuit, depending on what happens between A and B. So pause the video, try to understand yourself how this drawing here, how this schematics implements the XOR gate truth table. And I'm not even going to stop, right? If you want to stop, do that yourself right now. But the whole point here is, first of all, out of the bat, I see that this circuit that I'm showing is that naive one where the LED is not really in the output of the circuit, right? So this is just this standalone XOR implementation, right? We're gonna have to probably have more transistors, more than these 5 transistors already to implement the one that is like a pure output. But regardless of what we're doing, I think this one is important just for us to understand, right? So let's look at what this implements. I have the voltage coming here, either turning on the LED or not, right? Because if we find a better path and we find ground before the LED, then this thing doesn't get it up, right? Because if we enter through this path right here or this path right here, then we don't turn on the LED, correct? I think we should all understand that by now, right? If we have a path that is just easier to find the ground here or find the ground here faster than this one, then the LED will not turn on because we're going to reach the ground faster here or reach the ground faster here without having to go through all that trouble of lighting up the LED in the first place, right? So first things first, I think we all agreed that this one right here where we go power up the LED and we split between A and B transistors, right, with these A and B switches, this is an OR gate, correct? So this is an OR implementation. I think we all agree with that. This OR right here, the end output of this OR gets fed to this circuit right here. So we implemented the logic of the OR, but the output still has to go to this transistor right here. And this transistor will only complete the circuit and find ground and actually turn on that LED if this transistor is on. When is this transistor here on, right? When is this base of this transistor active? When we complete this circuit right here on the left. And what is this circuit on the left? Is the one that comes voltage, and we have those two transistors in series with each other. So if this transistor is on, and if this transistor is on, current will find an easier path and go straight down to the ground. It's not going to go and turn on this transistor on the right? It doesn't have to, because if we find a path here where this is closed and this is closed, if both these transistors are on, if both A and B switches are on, then voltage comes here, finds ground already, and we are done. So this is the kind of exclusion of that 1 and 1, right? If A is true and B is true, we already exclude, we come here, goes to the ground directly, and we don't have to power up the LED in the first place. We already bypass everything and we just go down. But if either A is false or B is false, then we go and we enable this transistor right here, which is the enabling of the OR gate output, which we just got from this implementation right here. Do you see? So it's basically this. I either exclude that option of when A and B are true, and then we just go straight to the ground and we don't go to the LED, right? This is the exclusion of that end when both A and B are 1. Or if either A is false or B is false, then we're going to go, current is going to enable this transistor right here, and this transistor is the output of the OR implementation gate that we just have here on the right. Good stuff? I think that's it. So I don't want to waste too much time right now with the exclusive OR gate. You know what? If you want to implement this thing using the simulator, if you want to implement using a breadboard panel or whatever you want to do, go ahead and do that. I don't want to do that. I just wanted to show to you the XOR gate and show the idea behind this implementation. But what I really want to do right now is I want to find some useful applications for all of these things that we are doing, right? It's a little bit dry. I'm just showing to you logic gate implementation, logic gate implementation. I want to show to you some actual useful applications for this thing. So where do we use this for actual computer stuff? And I think right now is a good time for us to stop, leave these logic gates behind. Well, not leave behind because we're going to use them extensively right now, but I want to use everything that we learned so far, and I want to start talking about computer devices. Especially, I think we're going to start with memory devices. So how do I go about storing in a computer a 1 or a 0, right? If I have memory, if I have a CPU register, how do I store a 1 or a 0, right? Just bit in memory. How do I store something using electricity? I'm talking about memory devices, not like hard drives or CD-ROMs or floppy disks, right? Not these type of memory devices yet. I'm talking about memory devices in terms of like RAM memory, for example, right? So how do I actually store a 1 or a 0 in a circuit, right? In this kind of 1 and 0 in memory, in a register, using just electricity. So let's just go ahead, let's just use everything that we learned so far, and let's just look at some applications. In this case, memory devices.